All right, what's up, guys? We're back again. I'm sure you're excited. To anyone who's been showing up, we appreciate you. None of us thought we were going to be teaching or making content, so we're just learning as we go. But we're going to get more interesting, better at being exciting, and less awkward doing this as we go along. So you just expect big things to come. We're definitely going to start upping some of the level of content that we bring to you. The goal is to start bridging the gap between some really complex journals and papers that require a lot of advanced math or even sometimes physics or just a deep knowledge in a subject and digest it for you and then sort of open up the possibilities for people to actually understand what they're doing without having to go through a math PhD to understand the whole paper. So look forward to that, but we'll still be doing some basic, intermediate, and advanced topics as well, but that's the goal. It's to move forward into giving you guys some great value and helping you make tons of money in the market, hopefully, even though this is all educational and none of it's financial advice. Today, though, we're going to be working with the Bayesian persuasion. The Bayes watch, as you can see, is going to be just the code portion of the Bayesian optimization, which is something that most quant traders have at least come across. And it's a great thing to keep in your back pocket because I think it makes quite a bit of sense. And realistically, I feel like if everybody thought like Bayes' theorem tells you to predict probabilities and updated their opinions as new information came in, we'd have a better world. It would save you a ton of awkward conversations at Thanksgiving with your aunt whenever she just is stuck in her ways and no amount of information can change her opinion on that political view she has. This is something that would just make the world a better place. And overall, I think it's a great tool when we're looking at hyperparameter tuning or just other use cases in the market. And so what we're going to start with is basically anytime you have some type of complex optimization problem where it's difficult to maximize or minimize the cost of some function, this is going to come into play. This is going to be, for example, nonlinear functions, really noisy functions, or computationally expensive functions. And that's why you're going to find this quite often in finance and in trading, because we have this random process that we're trying to predict that's ever evolving, and you just can't assume that the market's going to stay the same. You're pretty much asking to get blown up. And so after all our imports, I just copy and pasted over Bayes' theorem, which is the probability of A given B is equal to the probability of B given A times the probability of A, and then we divide it by the probability of B. Now I'm not going to go over how to derive this. You can go head over to our Medium article, which is going to be linked in the description, and it's going to give you a much more detailed breakdown of all the different functions we're going to be writing. Also give examples of alternatives to what we use here for an example, since this is meant to be just an easy overview. But basically with this, when we do Bayesian optimization, we have what we call the posterior, and that's equal to the likelihood times the prior, which is just this part. And then we take out the normalizing portion, which is what we divide by. And now this is going to give me an error, but we're going to just hop right into our coding because no one wants to hear me talk for that long. So the first part is we need some type of objective function, and this function is going to be noisy or complex, and so I'm just going to make one up. We're going to use some type of sine wave, maybe add a linear part and some randomness. And so the objective function is basically what we're going to use Bayesian optimization to try to estimate or approximate. And we're going to know what the actual function looks like because we just made it. But in the real world, you're probably not gonna. You're gonna have noisy data, and the goal is to kind of approximate this function. And so we're gonna make our objective. It's gonna take x, which is gonna more than almost always be a NumPy array. Since we're all traders here, I assume most of us are, we're gonna have volatility. In case later on I pass any values that aren't an array, I'm just going to do this now because I have a feeling that I'll run into that problem. And we're just going to make it an array if that's the case, if it's a single value. And so we're going to return some function that I'm just going to off the cuff build for no real rhyme or reason here. I don't know. We'll see how this looks. This is the best part. Every time I was in math as a kid and teachers would just come up with examples, it just seemed so useless. And now that I'm doing the same thing, I get it. So we have our objective function. I have no clue if this is going to look good or not. And we're basically just taking some sine wave, adding a linear component, and then some random noise. And if we put 0 here, then we're going to eliminate the random noise. It's going to let us actually see the function. So let's give this a plot. We'll do 5.01. Then we're going to take our objective, and this is going to have no noise. We're going to plot that, and then we're going to plot the noise version. And we'll scatter the noisy part. Let's hope I coded this well. All right. So there you go. We can increase the amount of noise that we're using. We can decrease it. But this is what our function looks like. And I'm just going to call it close enough to what the market is going to give us. And so now that we have this objective function and we have the noisy portion of the objective function, the scatter, our goal is to approximate that. And usually the way this is done is through some type of regression. You'll see a lot of Gaussian process regressors. You'll see random forest regressors. And there's many different ways and models that you can use. There's tons of papers out there. You could go look at any of the machine learning packages on Python. They'll link you to like a 200-page journal on almost every one of them. We're going to use one that tends to be used quite often, and it's the Gaussian process regressor. And that's just because it's pretty simple. And so this portion of the model is meant to approximate and predict the function. And so we're going to just make an approximate function. It's going to take the inputs and whatever model that we choose to use. You can swap them in. Like I said, we're just going to use one that's pretty standard, and partially because the default parameters on there work all right, just out the box. Now you can customize this function if you'd like, but for today we're just going to make it super easy. It's just going to use model and predict. And so now we're going to have x, again, 0 to 1. We're going to have y, which is going to be the noisy data here. Then I'm just going to call it y pure, so that we have the non-noisy data. We're going to reshape the data so that we can slap it in the model, have no issues. and model is equal to Gaussian process regressor. Then we're going to fit the model with the noisy data because this is what we want to approximate. We want to get a function for this data. And we're going to predict using our new function up there. And then we'll scatter the actual values, and then we'll plot our predicted with a line. And so as you can see, these are actual values. And this is currently what our prediction looks like. We're just kind of a nice trending upwards sine wave, which actually isn't that terrible. So this is where we start to improve on that. And the way we improve on that is a surrogate function, which comes in, well, we have our surrogate function, and then this is our acquisition function. And our acquisition function is going to have two parts to it. There's a part that looks through your search space of the domain of values that you can choose from. So whether this be parameters for hyperparameter tuning or some set of data, and it's going to narrow that space by selecting some portion of that should be the best or most likely to improve your model. And then it's going to use the acquisition function, which the goal of this is to basically say our current values that we're using in the model, what ones can I select that are probably going to have the highest impact in making our model better? There's a lot of different ways to do this. We're going to be doing expected improvement, which is a very common probabilistic version of an acquisition function. And there's several more that are mentioned over in our medium, and you'll get a better idea of sort of where to look if you'd like to swap some in and out. But this is a very common one. And for our search, we're just going to do a random search, which means we're going to randomly select some values within the domain space, put them into our expected improvement, and have our expected improvement tell us what is the expected improvement for these values. And then we're going to find the maximum of that. What do we believe has the highest impact in making our model better? And so the way we're going to do this is we're going to define our expected improvement, which is going to take our total data, then whatever new data, and our model. And so out of this, we're going to get the mean and the standard deviation of our model using model.predict, which will return the standard deviation. And then we have to reshape this. From here, we're going to have it predict the actual original data. We're going to find the max of this. And then we're going to get the z-score. Which we will then plop right into the maximum or the expected improvement function. Which, if you'd like to learn more, I recommend finding articles on, because it would take far too long for me to go over that. And there's several other, well, there's many more that you could choose from that would be just as good or maybe better in different situations. This is just a very common version. Just like with the next function, which is our search, our optimize the search, which will take x, y, and the model. This optimize search function that we're using randomly selecting samples, there are plenty of better ways to do this, but for simplicity's sake, when you review over this, this is probably going to make the most sense and be the easiest to digest the first time around versus having to learn some complex backbone to a function that makes no sense and add that on top of this whole thing. And so here we're just going to say random.random and get, let's say, 100 samples. And we're going to reshape it. As you can see, that's a common theme here. And now we're going to use our expected improvement, which is going to take x. It's going to take samples, which is that x new part of our function, and our model. And from here, we're going to find the index of the maximum score, and we're going to return samples. So we're returning that sample. And so now that we've built these, I can show you sort of what this is going to end up looking like when we do what all machine learners tend to do, and that's iterate over and over and over as we get hopefully closer and closer and closer to a maximum or minimum. And so here, let's just say 100 iterations for the sake of this video, not taking 17 hours. And then we're going to optimize our search. We're going to get the actual value for the noisy. And then we're going to estimate, which will be x and model. And the reason I'm going to put this estimate, and I'm not going to print it to keep it clean, but you could go ahead and print x actual and estimate, or you could find the difference, the mean squared error. You could keep them in a list and plot them later to make sure that you're improving after each iteration. This is mostly so that you can print it and make sure that it works. This would be my preferred way of going about this, because I'm not visually, when I look at a plot, sometimes it makes sense and it's very clear that something's getting better, but often I need to look at the data to make sure that I'm not just tricking myself. And in my head, it just works better. You might be more visual, but this is why we're doing it. In case you want to run it yourself, print it, kind of look at it and see what's going on. And so now, this is sort of where, when we go back up after, and I explain a little more, we're going to just add the x and y. Add the actual and add the new x, and then we're going to fit the model. And y. And so, what are we doing here? Well, when we go back up and we see this, what's so good is we're using the posterior to figure out the new data that's going to get added onto the likelihood, which is in return going to update the posterior. So when I was saying that most people should learn how to think like this, it's because nowadays everyone's so emotional and attached to an idea. But in reality, when I do something, I might be making a prediction with all the information that I have right now. But in the real world, you tend to learn new information as time goes on. And in something like the market, as new information comes into you, and time goes on, you're going to have different predictions and different probabilities because there's new data. And if you want to learn more about this, I cover it in more detail over in our Medium. But the gist of it is that we're just continuously searching the space, finding the value we think or the parameters that we believe are going to most benefit our approximation of the function. And then we're going to use that to search our search space, add that data back in, and over each iteration, we're going to learn new things, which in return updates our probability. And so there's plenty of ways that you could use this. It could help you decide whether you're going to take a trade. It could help you decide on hyperparameters. It could help you decide on your bet sizing, expected value. You could have a meta model for machine learning. There's all kinds of things that you could sit around and play with the idea of where you would need to constantly have an evolving opinion on something. And so here, we run through here, and now I'm going to kind of copy and paste over the plotting. And you can see that our model is looking quite a bit like it's looking very well with the noisy data. And so over thousands of iterations, you'd expect that we get quite close to making a good approximation function. And if you needed to see this in data or you had to see the improvement over each iteration, again, I would recommend you either print it or store it as a list. Now, one of the main cases that you might end up seeing it used for very often is going to be hyperparameter tuning. And in order to do this, I'm going to copy and paste the code I already wrote, and we'll just go over it really quickly to save some time, because we're going to go over how you would do it in a more manual way, and then how you can just take a module and use the Bayes search CV to do the exact same thing, which is what you would probably want to do in production unless you had some crazy changes you'd like to make. And so what we're going to do is just plop those in for anybody who wants to go back and eventually add them into their own and play around with them, which I always suggest you do. And so what we're doing in a more manual way is we're going to make the classification data. I just made some blobs. You're going to want to probably do it in a way that is using real data of some sort, but if you want to just learn, this isn't a bad way to learn. Then we make our model. I chose an SVC. You could choose plenty of different models. And then we're going to define our search space, which is going to be our hyperparameters, the parameters we'd like to find the best versions of. And in this case, we have our real, integer, and categorical. And then we define the name, which this is the parameter. And so we're doing this range in a log uniform scale, this range for the degree, this range again, and then we're picking between one of these categories for the kernel. And so use namespace or named arguments, we add search space, and then we define a function that takes these parameters, puts them in our model, defines some type of cross-validation, which I just chose this for an example. And then we get the cross-validation score of the model, the data, or cross-validation, and I said we're scoring by accuracy. We get the average of this result, and we return 1 minus this estimate. And from here we can use GP minimize, put in this evaluation function that we just made and put in the search space that it's going to evaluate over. And it's going to give us the best results where we can get our parameters and we can get the accuracy of that. And so this is how you would go about in a more manual way. I'd only suggest doing this if you have anything that you actually want to, either you're tinkering with it and you want to understand the concept more, or you have some type of improvement or innovation you'd like to add to it. If you just want to use the simple generic version, which is likely to have less bugs, less issues, and just work better overall, then you can do it in far less steps, way easier, by just using the Bayes search CV. As you can see, the parameters are the exact same. The only difference is the name is now a key. We make our cross-validation. We have this Bayes search CV, which we add our estimator, our search space, and our cross-validator, and then we fit it. And you can get the same stuff out of that. And it's much easier. So I recommend you use that for sure, unless you want to just create and innovate, which by all means, go for it. But hopefully that helps give you an idea of how to code something like this and what the objective is and how we're using updating data to update our view or the probability that we're predicting. And hopefully it's gotten some wheels turning with how you might apply this when going into trading, since there's plenty of different ways where you could apply this. There's many use cases. It's a very good thing to have in your back pocket. You'll see it used for all kinds of stuff. And our goal here is just to give you a basic overview. Again, our Medium article is going to go into more detail on almost all these videos. This is just so you can watch, code along, hopefully add a little bit of value in the fact that it's a video, and some people really just don't want to read. But on that note, give us a like, follow, subscribe, tell your buddies. We're going to be doing some pretty big things in the near future. We have a good team, and the consistency is going to pick up. We're going to get better at actually recording these videos and being entertaining. And we appreciate anybody who's watching. From the beginning, you're going to be the OGs. And get out there, apply this. Hopefully come up with some brilliant ideas and make racks. That's the goal. That's what we're here for. We want to make this quant trading stuff a little more accessible to those people who are really smart and just want to learn and don't want to YOLO on technical analysis and just gamble. People who actually want to make a name for themselves in the space. But we appreciate you guys. We'll see you next time. Should have some videos coming out this week.